Okay, in this video we're going to balance this redox reaction in an acidic solution. The nice part about these acidic solution ones is it's fairly easy to see what elements will be the ones with the changing oxidation numbers. Specifically here we have oxygen in compound with 2 times a -2 charge, so that's -4. It's a neutral element, so that means the lead will have an oxidation number of +4. So lead is going from +4. Here lead is on its own with a charge of +2. To reduce the charge from +4 to +2, we can see that 2 electrons will be needed, or if you prefer to think of it this way, +4 plus -2 leads to +2, so that means the charge is conserved. So that identifies the lead as the object, or as the element that's changed oxidation numbers. Now looking at the iodine, anytime you see one as an element on its own, you know that that's going to have a changing oxidation number, because if it's in an element and then it's in compound later, then when it's in compound it's very likely to have a non-zero oxidation number, so 0 to something. In this case, the 3 oxygens have a -2 oxidation state each, 3, and that's going to total to a charge of -1. So whatever iodine is has to work there as x. So I get x minus 6 equals -1, or x equals 5. So here the iodine is going to a charge of +5. If I have 2 of them in its elemental form, and they're going to perform +5, that means I need 2 iodines to break up to +5 each. If I recognize then how many electrons are going to be required or produced in that process, if I keep in track of this as a total charge of +10, 2 times +5, I go from 0 to +10, that means that I must have released 10 electrons to make that happen. Here I have 10 electrons feeding into 2 electrons, so I have 8 extra electrons that aren't going anywhere right now. What that means is I'm going to multiply my lead half reaction by 5. That'll change my 2 to 10 electrons. Put a 5 on both of these leads. And then I have 10 electrons matched up with 10 electrons. 10 electrons in, 10 electrons out, and they agree with one another. So this lead is this guy right here, and this lead is this guy right here. And this I is this I right here, and it has nothing on it. So I'm going to put a 1 just to show that I've balanced it, or that I've considered that species. And this I plus 5 is right here, and he has a 2, as is shown in this half reaction. So there we go, that's our equation. And that's it balanced for electron transfer. Now what I'm going to do actually is I'm going to erase all of this stuff, and then as a result I'll be able to re-see the equation well, and be able to balance the waters and then the hydrogens. So I'll just erase that. Now, here I can see I have 10 oxygens on the right hand side. I'll just put oxygen so it doesn't look like a 0. And here I have 6 oxygens on the right hand side. And so I'm missing 4 oxygens here. That means that I need to add 4 water molecules, 4 H2O. Having done that now, I can balance my hydrogens using a hydrogen ion. I have 4 times 2 hydrogens on this side, and that means I need 8 hydrogen ions on my left hand side. If I've done this correctly, the charge of both sides should be equal to each other. No charge, 8. So this charge has this side has a charge of +8. Plus 10 from the lead, minus 2 from the iodate. And so this side has a charge of +8. And so since +8 equals +8, I know that I've balanced this equation correctly. So that is balancing in an acidic solution.